学术先驱的奠基下，河南大学地理学科逐步发展成为涵盖人文社科、理工学科等多学科交叉融合的综合性学科。历经100年岁月洗礼，河南大学地理学科已构建起以黄淮流域地域特色为根基，融合地表圈层要素综合研究与空间信息技术集成的学科体系。王家耀院士、张晓烨院士、刘彦绥院士等一大批专家学者汇聚于此，以智慧力量赋能中部崛起与生态文明建设。党建领航，赋能学科发展。河南大学地理学科先后获批全国先进基层党组织，首批全国高校黄大年式教师团队，全国高校100个研究生样板党支部，全国党建工作标杆院系，地理科学专业获国家级教学团队等荣誉，为学科发展注入强劲动能。培植沃土，书写育人新篇。河南大学地学人砥砺深耕，在国家级竞赛中屡获殊荣，以优秀教材、国家级课程开发，全方位赋能学生成长和人才培养。科研创新实现国家级奖励突破。2021年，王家耀院士斩获国家科学技术进步奖2等奖，荣膺中国地理学会科学技术奖、终身成就奖和河南省科学技术杰出贡献奖。刘彦绥教授获批国家自然科学基金重大项目，乡村地域系统协同观测与转型机理及模拟。河南大学地理学科在国家级重大重点科研项目上屡创佳绩，凝聚专业知识，服务国家战略。科研团队主动服务国家重大战略，构建核心技术体系，研究成果得到国家领导人的高度认可并批示。发展至今，河南大学地理学科已形成党建引领、人才筑基、科研突破、服务赋能的良性发展格局，拥有地理科学、人文地理与城乡规划、地理信息科学、环境科学、测绘工程5个本科专业，打造空间智能、遥感智能2个特色方向和地理科学工程实验班，培养了2万多名毕业生，遍布科研院所、企业和政府单位，成为服务黄河流域生态保护和高质量发展的国家战略的重要创新策源地。连续多年推出422地球日等一系列特色地理实践活动，组织学生参加英国、爱尔兰、澳大利亚等国际联合实习，获批国家留学基金委大河文明与可持续发展国际暑期学校，与北京大学等开展黄河流域自然地理综合实习。品牌活动在 Global Times 等权威杂志报道，持续提升地理专业影响力。立足100年地学文化根基，创建了全球首个地理科学与工程学部。学部整合多个学科，凝练6大方向，构建地理科学、地理技术、地理工程3维创新体系，打造社会经济发展新质生产力，营造基础研究、技术攻关、实践应用全链条生态，创建以交叉型、综合性、工程化为特色的河南大学地理学科建设新机制。
And since this time we have a friend coming from Germany as our audience. Um, Will you kindly agree with the talk in English? And before the talk, I'd like to briefly introduce Brillouin. The Brillouin Chen is an associate professor in the Department of Physics at Southern University of Science and Technology. He received his bachelor's degree in mathematics and physics from Tsinghua University in 2012, and his PhD degree in applied physics from Stanford University in 2018. Then he conducted research at Stanford University and SLAB, National Accelerator Lab, as a postdoc. And he joined SUSPAC in 2022. Concurrently, he serves as a PI at the Quantum Science Center of Guangdong, Hong Kong, Macau, Greater Bay Area, while he also acting as an editor, superconducting materials and physics of cuprates and nickelates. I think most of us are familiar with Professor Chen for his work in the field of lanthanum-327. And today his talk is ambient pressure, superconductivity, and electronic structures of the engineered hybrid nickelates. Let's welcome.
Thank you very much for the introduction. It's my great honor to come to Nanjing University again to give a talk. So last time, I guess it's on the same topic, but recently we have already some more recent results. So it's a great pleasure that we have this chance to share some of our very recent results here. Before starting, I would like to first acknowledge Professor Qikun Xue for the leadership and great support for the entire project. And some of the data that I will discuss today is in very close collaboration with Professor Junfeng He from USTC and also Professor Dawei Shen from USTC. So high TC superconductors for decades is dominated by two main families. Basically, these are cuprate superconductors and these are iron-based superconductors. And Nanjing University is a hub to for both of these superconductor, the research and investigation. So these two families are quite different. For cuprate superconductors, it has a 3D9 electronic configuration, and near the Fermi level, the most important orbital is this 3D dx square minus y square orbital. And for iron-based superconductor, it's quite different. It's a 3D6 electronic configuration, and it is a multi-band electronic structure near the Fermi level. It's a 3D xy, 3D yz, and 3D zx. These three orbitals. And quite recently, since 2019, nickelate become superconducting. And nowadays, there are actually two quite distinct type of these nickelate superconductors. One type we can call it square planar. This type is actually first discovered to mimic cuprate superconductors. You can see this this structure is very similar, almost the same. And also electronic structure, it is also 3D9, also 3D dx square minus y square orbital is dominating near the Fermi level. And also both this cuprate and also the square planar nickelate superconductors, it has pretty strong correlation, electron correlation. So it's governed by this charge transfer gap and also this mod gap in these two types of superconductors. And for another type, called this Ruddlesden-Popper type. It's actually very different from this square planar, mainly because the existence of this apical oxygen in between this nickel oxide planes. And also, of course, outside this nickel oxide plane, there's also another apical oxygen. In material-wise, if you oxidize this square planar, you will get this Ruddlesden-Popper. And if you reduce and remove the oxygen, you will get this square planar. But the electronic structure is dramatically changed because of the existence of this apical oxygen. It is in between 3D7 and 3D8, and also it is a multi-band system near Fermi level, including the dx square minus y square, and also the dz square orbital in play. The nickelates are discovered so late if you compare with the cuprate or even iron-based. Actually, the idea to find superconductor in nickelates can be dated back to like for decades ago. But only very recently we achieved the superconductivity in this type of a material, mainly because this type of material is really actually notoriously difficult to treat, difficult to handle. The two extreme square planar type and this Ruddlesden-Popper type are actually two extremes of the materials in terms of oxidation. This square planar needs a very strong reduction to remove all the apical oxygen to get superconductivity. And for Ruddlesden-Popper, you need to put all the apical oxygen back to the lattice to make it superconducting. And actually, both of the full oxygen, fully oxidated state and the fully removal of all oxygen, apical oxygen, both of them are not so thermodynamically stable. So for both type of materials, we need to push to a limit that's beyond the stability of thermodynamics. So it's very difficult in the sense of controlling oxygen. And another type of difficulty is the crystalline structure control. If you look at this whole series, for example, from this 4-3-10 structure, the cation ratio between rare earth and nickel is 4 to 3. And the one next to it is 5-4-13. It's a 5 to 4. This ratio difference is quite small. And so if you're not controlling the growth or the synthesis parameter so accurately, you will have a lot of intergrowth and different phases within the same crystal you grow. So it's also very difficult to control the crystalline structure. And some are superconducting, some are not. So we also create this difficulty to differentiate which type is superconducting or which type is not. And so it's a difficult material in many aspects. Yeah.
When you make the sample, you control the ratio between the R and the nickel.
Yeah.
Or you control the growing parameter.
All of these aspects, you need to control them perfectly. Yeah. So this is why it's so difficult, and people are discovering this so late. Yeah. Coming back to electronic structure, cuprate and the square planar nickelates are quite similar. This is 3D9, and you can see dx square minus y square is at the top. And square planar nickelate, take the infinite layer for example, it is also similar. but there are some difference mainly coming from the 5D orbital or the interstitial s orbital. But that's if you only consider this nickel orbitals, it's very similar to the cuprates. Yeah, and but for RP phase, Ruddlesden-Popper phase nickelates is very different. Take this bilayer as an example. Because the existence of the apical oxygen, the two nickel oxide planes are coupled so intimately. So you need to consider both planes together, and so you can see these states are doubled. The number of these states are doubled, and also the important stuff is this dz square orbital because it coupled with the pz of the apical oxygen so nicely. So there's a hopping between these two planes is pretty strong, and then you get a bonding state and anti-bonding state. It's quite well separated, and if you count the number of electrons near Fermi surface, Fermi level, the dx square minus y square is still there, but this dz square is very close to the Fermi level. So the question we want to ask is, can we experimentally probe and also engineer the electronic structures of the superconducting nickelates? So my talk has 3 parts. The first part is about growth methods. So our growth methods is a little bit unique. So it actually enables all the developments afterwards. Second part is about how we utilize this growth method to engineer different hybrid superstructures and to realize the systematic RPES band structure measurements. And then the third part is about how we use this unique growth method and take advantage of this growth method to realize the TC enhancement to above 60 Kelvin. There are 2 mainstream oxide epitaxial thin film techniques. The first one is people call it oxide molecular beam epitaxy, or OMBE. It has a pretty good structural control precision. It can do deposition atomic layer by layer by using these different shutters for different different cation sources. And but it has a limitation. The chamber pressure for this method cannot be too high. If the chamber pressure is too high, the evaporated material, the mean free path of this evaporated material will be shortened, and then nothing is going to deposit it on the substrate. So considering the deposition rate, you need to keep a chamber pressure at a pretty low condition. And so for this limitation, people need to use a stronger oxidant. For example, ozone or plasma oxygen or atomic oxygen for OMBE in many cases, if you need a stronger oxidation power. And for PLD, if you use a single target for the growth, the material is excited by this pulse laser. The material absorbs the energy of the pulse laser and become quite high energy and becoming a plasma. The plasma has a pretty high kinetic energy, so it can go through higher chamber pressure. It is tolerant to a higher chamber pressure. But typically, if you use a single target for the PLD growth, meaning the thin film chemical composition is similar to the target chemical composition, then usually the growth precision is unit cell by unit cell. so it's not as accurate as the control of OMBE. Another route that's not so mainstream is to use different targets to do this similar PLD stuff. Someone called it atomic layer by layer laser MBE. This technique can be dated back to the late 80s when the cuprates are just discovered. So they use different targets, for example, bismuth oxide, strontium copper oxide, calcium copper oxide, different targets, and successive deposition using this laser ablation, they can control the structure of visco. And more recently, this is also applied to the nickelates in the last decade. So they can, Xi Xiaoxing from Temple University, they can also grow pretty good Ruddlesden-Popper nickelate phases. And the difficulty of using this, the reason that this is not so mainstream, maybe is because of the control is actually quite difficult to do because you need a very good automation to really do switching this target, and also the degradation of the target is also difficult to maintain. So anyway, we build on this basis. Building on these all these bases, we developed this technique that we call gigantic-oxidative atomic layer by layer epitaxy, or GAE. This method combines purified and concentrated ozone source with the automated target and laser energy switching. So it's a highly automated, and also the oxidation power is very, very strong. First is to use a highly purified ozone. So this actually we have put in a lot of effort to make the ozone really pure, and even within the chamber, it can generate a concentrated zone and also very strong oxidation. Ozone is known to be very easily decomposed to oxygen, and so in the transport of ozone, when you first purified it using this liquefaction way to purify this ozone, and then the ozone evaporated and transferred to the chamber, all along this way is decomposing. So we put in some effort to make the ozone, even inside the chamber, it still have a quite high ratio. Yes, yes, yeah. And so ozone, when the ozone is coming in and hitting this hot thing, the substrate is hot under growth condition, it decomposes again and also be reactive here. So ozone is decomposing all the way along. Even so, if we use RGA to detect the ozone concentration on the side of the chamber, we can still get above 10% of the ozone, and also the atomic oxygen, because the ozone will decompose to oxygen molecule and also atomic oxygen. The real oxidative stuff is the atomic oxygen. So even after so many decomposition along the way, and also the reaction at the surface of the substrate, we can still get above 10% at the side of the chamber. So it's a really highly purified ozone. And then by this method, we achieve a much larger growth parameter space comparing to OMBE. If we compare to PLD, here we compare to the PLD with oxygen. In principle, if you use PLD with ozone, you can also go to similar oxidation strength. But with all this careful treatment of the ozone, but the deposition precision for PLD is slightly lower. If you compare this GAE with atomic layer precision and oxide MBE, basically it has more than 10,000 times of the stronger oxidation. And yeah, in our second generation of this system, the first generation is combining the parts imported from Netherlands, and some parts are made in China. And in our second generation, the whole system is made in China. So with this GAE method, we can successfully synthesize a whole series of lanthanum nickelate RP phases from n equals 1 to n equals 5. This is actually not new. So we are also following what has been done by many groups, including Nie Feng's group and also groups from the US. But we can achieve a very high quality film. Take an example of this 5-layer version. So you see this unit cell is pretty big, and within a limited film thickness, like 16 nanometer, there are not too many periods of this unit cell that you can get from the diffraction. But still, from 10 degree to 80 degree, this very wide range, you can obtain every small peaks that you expect to see in the X-ray diffraction. So that signifies quite high crystalline quality. So we can achieve a pretty good pure phase of this bilayer type. So that's just one key of achieving superconductivity. There are 3 more very important keys. First is to use the strontium lanthanum aluminate substrate. So this substrate gives you the right strain to about 2% compressive strain to achieve this the strain that is appropriate for superconductivity. And the third key is ultra strong oxidation, and this is exactly that we are our GAE method is good for the ultra strong oxidation. And the fourth is the praseodymium substitution. The exact role of praseodymium, I think, is still under discussion in the field. But from our experience, it's pretty interesting. If you don't have praseodymium, you can still have superconductivity, but not so good. Even if you add very, very small amount of praseodymium, in this our first report, we actually only add 5% of praseodymium, and then we can get much better superconducting property. So we guess the ionic size may be important, but maybe more important is its integration with oxygen is better, the praseodymium. So we achieve this zero resistance and also diamagnetism within the same sample, and also the onset temperature is slightly higher than the McMillan limit. And this is a definite proof of superconductivity at the ambient pressure. Stanford also reported similar signatures using a different method, the original traditional PLD method. So both these results together confirm that the Ruddlesden-Popper nickelate superconductivity under the ambient pressure in the thin film form. So beyond this simple bilayer phase, we can also engineer hybrid structures taking advantage of this our GAE method, this atomic layer by layer growth mode. So we can do structures like this 1-2-1-2. This 1-2-1-2 is consists of a single layer, bilayer, single layer, bilayer alternating. It's like a super lattice stuff. Actually, in last year, like in the middle of last year, we can already make this structure, but at that time we didn't get superconductivity yet. And so more recently, we beyond this 1-2-1-2 and now we call it 2-2-2-2 in this series. This is the bilayer 3-2-7 superconducting stuff that's established just now. We also did 1-3-1-3 and 2-3-2-3 structures. This 1-2-1-2 is actually also synthesized in bulk form and achieved in superconductivity is achieved under high pressure. And this 1-3-1-3 is same chemical composition variant. The structure is completely different from this 2-2-2-2, but they both are 3-2-7 in chemical composition. And for this 2-3-2-3, maybe it's more difficult to synthesize in bulk form. But for using this thin film method, atomic layer by layer thin film method, we can construct this complex superstructure. Pure trilayer is easy to grow. For example, here, this is the trilayer compound. This is not difficult to grow, but if you do it casually, it's not superconducting. But if you want to conclude that this structure is not superconducting under this strain, it's more difficult. If something is superconducting, then that's superconducting. But if you say that it's not superconducting, maybe it's just you're not good enough, right? So you need to be very cautious and do everything you can to confirm that it's not. It's, yeah, maybe, yeah. So in our lab alone, we cannot apply this C direction pressure, but maybe collaborating with the other groups, we can try this uniaxial C lattice constant shrinking, right? This film is tetragonal. Yeah, this we characterize. I didn't put the oh, I have a figure afterwards for the 60 Kelvin stuff, but this thing is tetragonal for sure. Yeah. It's easy or what? Yeah. If you have the face cation face on this substrate, it appears tetragonal. Yeah. So recently, the Stanford group reported the result on LAO. They can also make it superconducting, but with a much lower TC. And so I also asked Yijun whether it is tetragonal or not. I think he is still trying to characterize accurately whether it is tetragonal or not. Yeah, maybe it is, but maybe it's on the boundary. Yeah, so these are the 4 design structures, and the results are showing that we get the desired structure. So this 1-2-1-2, you can see this bilayer, monolayer, bilayer, monolayer, bilayer, monolayer. Also in the EDS, you can see 2 layers of nickel and 1 layer, 1 layer alternating. Yeah. So 2-2-2-2 is all bilayers. 1-3-1-3, you get 3-1-3-1 alternating, and 2-3-2-3, you get 2-3-2-3 alternating. Yeah, these are smaller range TEM. Green? This one? Lanthanum praseodymium is this, yeah.
All these 4 structures looks nicely. So far only the
no. 3 show superconductivity. So 1-2-1-2, 2-2-2-2, and 2-3-2-3. Yeah, superconducting, and 1-3-1-3 is not superconducting. Yes. So that's a very good question. For these 2 structures, after growth optimization and all the process optimization, we can get a pretty good single transition. And for this 2-3-2-3, at least for now, many of our samples are all showing these two transitions. And another interesting thing is the TC for the first one is about 45 to 50, but this second one is always in between 10 to 20, this range. Yeah. That's also insulating, highly insulating. Yeah. We don't know yet. So why this is so? Yeah. So I guess quite a few colleagues comment the same thing. Yeah, this second one maybe is trilayer superconducting, but personally, I guess it may be proximatized by the bilayer or some incipient kind of a superconductivity. This 2-3-2-3 structure, since you have a metal of trilayer in between, the communication, the coupling between the bilayers is actually a larger distance. Yeah, so it's even harder for bilayer only to achieve phase coherence, the global phase coherence among all the areas of the film. So the trilayer need to do some need to be the media for phase coherence. Mm-hmm.
First report film statement was that it's you can achieve maximum just 1 or 2 layers, and then the mismatch between unit cell. So one is actually just the 2 unit cell.
Yeah, that's a very good question. So I guess the relaxation of the strain happening around 10 nanometer scale. Yeah, and so below 10 nanometer is still okay. So for most of our film is optimizing under 10 nanometer. We didn't have enough time yet to do this relaxation and thickness dependence study yet. Yep. So mutual inductance, Meissner effect, can also show the 3 superconducting, and 1313. This one is not superconducting. So yeah, if you look at this 2323, it shows some diamagnetism, but at a quite low temperature. It's actually matching that the zero resistance is at a pretty low temperature. But for this 2222, it has a it's a quite big improvement compared to previous reports. So this is the first report from Stanford. This is our first report, and this is the second report from Stanford, and this one is our most recent data. So you can see the diamagnetism is saturating at the approaching zero temperature, and also it's quite close to zero already. This discrepancy, may be coming from the leak of the magnetic field from the side of the film, because the films is 5 by 5 millimeter, and this thing is about 2 millimeter. So there is still some magnetic field is escaping from the side of the film. Yep. So after determining the superconducting property of all these films, the next mission is to measure the electronic structure, the band structure of all these 4 different structural variants. But this is this is actually a pretty difficult mission, because of the oxygen is not that stable inside the structures. For example, this is a result from the bilayer. If you put the sample in vacuum, it's gonna the resistance is gonna go up gradually. It's in the hour scale, and this is mainly because of the oxygen loss from the surface, and also underneath the whole film is gradually losing oxygen, so you get a higher and higher resistance. It has a limit. If you go lower than 200 Kelvin, basically it doesn't change by time. So we invented together with Junfeng from USTC this cryogenic UHV seal case. So this is already the second generation. The first generation is using liquid nitrogen. Using liquid nitrogen, you have to carry a tank of liquid nitrogen all the way along, so you can only drive with this seal case. Now this second generation is using this completely dry method, Stirling stuff, to make it under 200 Kelvin. It's the base temperature is 100 Kelvin. So the samples after growth, this seal case is directly connected to the growth system, and then after the growth of the sample, it's basically quenched to below 200 Kelvin immediately. So this is to preserve the surface of the sample. We are sure that the surface of the sample is have no oxygen loss. It's superconducting, and also this whole UHV condition can preserve the quality of the sample surface for RPS measurement. So the 4 different structural variants have actually quite different RPS results. For the first 2, the 1212 and 2222, they are qualitatively similar. If you look at the Fermi surface, you basically can see both all of these alpha, beta, and gamma bands. This gamma one is around this Brillouin zone corner. But if you look at the spectra, you can actually see that around this Brillouin zone corner is actually quite bright and all the way bright. It's harder to resolve this kind of line feature. If you look at this band structure, energy versus momentum, you'll find that there is a very straight feature, a vertical feature that's actually the brightest one, brightest feature in the spectra, very near this Brillouin zone corner, this M point, in both this 1212 and 2222. So if you look at these two spectra alone, there is no way that you can figure out what's happening. What's this very bright and no dispersion vertical feature? Only when we see this 1313, you can see that this in the 1313 case, the flat band is below the Fermi level, and then there is a vertical feature below this flat band top. So we don't know the exact origin of this vertical feature, but it appears at least kind of associated with the flat band top. So if you look at these three together, maybe you can speculate that there is a flat band top above the Fermi level, and then this vertical feature is the waterfall like this from the flat band top. So this speculation is actually further enhanced or further supported by this measurement from the 2323 structure. The 2323 structure actually we can observe both these two features together, and it's more clear in this polarization dependence data. You can see that both this gamma 2 that's crossing the EF and also this gamma 3 that's lying below EF are showing together. And also,
what do we have when you have gamma 2 and gamma 3? Are they both bounding back, or one of them are bounding and the other kind of non-bounding?
Well, the exact origin needs theories to help us understand. But our very naive and simplified understanding is that the gamma 2 may be coming from the bilayer structure and the gamma 3 may be coming from the trilayer structure. Yeah. So also this polarization dependence between LV and LH help us to understand that both this gamma 2 and gamma 3 is coming from dz square. Yeah, because for LV, the dz square is going to be enhanced, the intensity. So by comparing all these four different structures, we get a basic understanding of what band structure or what Fermi surface is for the superconducting samples, at least for our samples under this consistent compressive strain and also this oxidation condition.
So the experimental results suggest that the unband is essential. For the 2323, you have a two-state. You also related to this gamma.
Yeah, we need theories to understand.
Something like the gamma band, but so do you also look at the second derivative to identify these points? Because if I would just look at the spectrum, it's very hard to really see the two gamma bands. So
I think it's already not hard to see here. Yeah, you can. The right hand side, maybe we should put this on the right, but on the left is actually much clearer. So there is a bright thing, horizontal thing, it's actually pretty clear, I think. Yeah, and in this screen maybe, yeah, it's I think it's still visible. But for RPES measurement, usually this is for like a visual. This black and white stuff is for like a visual thing. If you really want to get the exact position of these points, you usually look at MDC and EDCs. Yeah, the momentum distribution curve and the energy distribution curve. So these points are you find this peak of this MDC and EDC. Yeah. Yeah. So right. After getting the band structure, next mission is to measure the superconducting gap. So for nickelates, there are three possibilities. One is S wave, and then dx square minus y square wave, and dxy wave. These three possibilities will give you different measurement result from RPES. For S wave, you get finite gap along all the Fermi surface, and for dx square minus y square, because you have a sign change across this 45-degree diagonal direction, so you will have a node at this point. So the dxy is basically a rotation of 45 degrees compared to this dx square minus y square. So in the cuprate case, basically all RPES measurement is same as this scenario. So it's the RPES in cuprates is a very strong evidence for this D wave superconducting gap. So for nickelates, the first thing to check is to check this 45 degree. 45 degree, we see quite clear gap with the superconducting coherence peak. So it looks very similar as a superconducting gap. It looks like a superconducting gap. Another feature is this backbending. Usually, if it is a superconducting gap within a finite range of momentum near KF, you should see a backbending, and we can also see this backbending. And also within a range near this 45 degree, we see this superconducting gap with the coherence peak in all these cases from 42 degree to 50 degree. This set of data is obtained in Junfeng's lab in USTC with the laser RPES. Temperature dependence, I have a slide. Yeah. So laser RPES has very high resolution, but it has no access to the boundary of the Brillouin zone. And so we also conduct this synchrotron RPES measurement to get the results from the boundary of the Brillouin zone. And so the result is basically consistent with the laser results in the range that laser is accessible. And outside with larger degree in the beta band, we can also see a gap. And also in the gamma band, we see a finite gap in all the directions. So combining these results, we can say that the superconducting gap is finite in all these directions in the Brillouin zone, including this diagonal 45 degree, and also the 90 degree or 0 degree. So this is inconsistent with the dx square minus y square or dxy wave symmetries. And it may be consistent with S plus plus or S plus minus.
Why the gap on the alpha part? Or the alpha part is not that?
So at this in this measurement, we are not confident enough to say that some gap. What's the gap size of the alpha? Especially in this direction, in laser RPES, the intensity is quite weak. So we are not confident enough that we can get a concrete result of a gap size. So we choose to be conservative. Fermi surface can be clearly seen in some cases, not all the cases. If, for example, here, in some cases you can see the alpha, but because it's so close to the beta, and we need better data to be sure about the alpha band. Matrix element effect. Yeah. Sometimes it's more brighter. Sometimes it's not bright enough. Yeah. So it just takes more time to find the right condition to measure. There are a lot of constraints. If you go to a synchrotron, sometimes the resolution is not high enough for some photon energy, and some polarization, the fluence of the photon is low. So there are a lot of constraints, and also it's also related to the beamline system. Yeah. Right. Temperature dependence. Yeah. So this is the data we just seen at 10 Kelvin. You see gap and also coherence peak, and at the higher temperature, you see some dip. Looks like a gap, but no coherence peak. So to understand this quantitatively, we can measure this depth of the dip of the gap, and as a function of temperature is plotted on the right. So from 150 Kelvin, when we decrease the temperature, you see first a gap without coherence peak, and then under the TC onset, you see another very quickly dropping gap happening, and also with the coherence peak. So this combining the existence of coherence peak and the backbending behavior and this temperature dependence correspondence to the TC, we can say that this should be a superconducting gap. But for this gap without coherence peak, it's hard to say what it is. We can just say it's a pseudo gap. But whether it's the same as the pseudo gap in cuprate, we are not sure. Energy scale, it's about I guess it's not well defined, but about like 20, I guess. Yeah, the superconducting gap is close to 20. Yeah, so it's slightly larger. Yeah, so 30, 40, that kind of scale. Yeah.
I have another question. I mean, this is a symmetrized data. At the same time, we know that extremely much proportion, so it's just a little bit touches the Fermi level. So in this regard, one would expect that it's a gamma band because in the Fermi level, then generally your density of states has to be extremely particle forward symmetric with respect to the Fermi level. Nowadays we cannot see it because we only probe the occupied part. Now it's a different question because in the data of the group of type event, they don't see such a large activity. It would be expected the gamma band would be present. But I have another question. The question is, could it be that the gamma band, because in principle it's so close to the Fermi level that it also will be sensitive, temperature dependent, effective chemical potential, because the gamma band will be temperature dependent. So could it be that what we follow suit again, it's just kind of provocative question, that effectively just the result that the gamma band is strongly temperature dependent, because you would expect in this situation when the flat top is so close to the Fermi level that it's actually also temperature dependent, and essentially what we follow suit again could be simply a result of the change of the shift of the slight shift of the gamma band with respect to the Fermi.
I appreciate that comment. So whether the gamma band is really so close to the Fermi level, I am not completely sure. So for example, in these cases, some are actually not so close. If you look at this one, the gamma pocket seems to be quite large, meaning maybe the top is like slightly higher than like very close.
But there you give some, right? In the cartoon, you put the scale, so you know where the
This cartoon is completely just cartoon. It's not, yeah, it's qualitative, yeah. Yeah, maybe we can try. But generally, our attitude to this data is that it's not completely quantitatively accurate. A lot of the feature we are sure that it's qualitatively there, but if you want to do very accurate quantitative analysis, maybe the data quality is not enough. Yeah, right. You can definitely do something. Yeah.
Known that uniform susceptibility is a measure of the temperature dependent shift of the electron in four pockets. So that means that if you measure uniform susceptibility or uniform magnetization above Tc, usually in the metal it should be Pauli like, which have a constant, or if there are some local moments, it will be 1 over T. But in the case if there is a kind of part of the Fermi surface pockets which are changing with the temperature, you can try to measure as a function of temperature to see if you also see a kind of a pseudo gap in that case.
Okay.
I don't know whether it's easy to measure or susceptibility.
The best thing is that because this pocket is so shallow.
Yes.
The Fermi energy of that shallow pocket is very low.
Yeah, right. And so the mu is changing.
Then it temperature changing. The mu is new.
Yeah, right.
Yeah. If you do the momentum dependence of the structure, it also shows this problem. You only show one direction of.
Right. Yeah. That takes time. Yeah, right. Okay. Yes, another important stuff from cuprates and also iron base is this sometimes called kinkology. It's because of both bosonic mode coupling, the band structure is renormalized, and then you see a kink in the band structure from RPES measurement. So if it's DFT, you see it should be pretty straight in this regime. But in RPE's actual measurement, there is definitely a kink. And this kink is it should be a result from bosonic mode coupling. And the energy scale is about 70 milli eV. And from different analysis, you can all see this kink with this MDC full width half maximum, and also the position of this kink. And also in EDC, you can see the existence of this kink. Yeah, so this bosonic mode is there, and maybe related to pairing mechanism or not. So it's also under discussion.
See this peak. Is that something like having peak pump?
This is not peak deep pump. Yeah, so it's just there's obviously an anomaly around here. Yeah. This feature is also seen in cuprates. Yeah. Yes, but this is a higher energy scale, so maybe it's not related to the gap measurement. Yeah, it should be above this. It should be exist, but we may need more time to measure high temperature data. Yeah, but in cuprate and in iron base, these are measured a lot. Yeah. Right. So comes to the last part. So how to get this 60 Kelvin enhancement. So this is in our understanding, I think this is very related to a fundamental thermodynamic dilemma in the synthesis of these superconducting Ruddlesden-Popper bilayer films. So that is the hyperoxygenated state that's essential for superconductivity is actually thermodynamically incompatible with the stability of the bilayer crystalline phase. That means the thermodynamic condition for a good crystalline phase is not the same it's not the same as the requirement for the oxidation state required for superconductivity. So to decouple this conflict, people usually what people usually do is to use a two-step strategy for PLD or for OMB methods. First, you grow this film under a condition that's good for the structural stability. You get the bilayer structure first, and then it is an insulating film after you just grow this structure, and then you use a very aggressive post-annealing step to force the oxygen inside the lattice to make it superconducting. So that's a two-step process to decouple this conflict. And by our GAE method, we push to an extreme. So this is a highly non-equilibrium condition. It is a very, very high, oxidation condition, much higher than both PLD and oxide-MB, and also a much higher growth temperature. This is 850 degrees C growth temperature. And so also it is atomic layer by layer, this kind of growth mode. So by pushing it to this extreme limit, we actually achieve several things together. So first is the oxidation state. Right after growth, the film is already superconducting. We don't need any post-annealing process. And then secondly, the crystalline phase, the structure is still bilayer and very good quality bilayer. It's actually greatly enhanced this bilayer structure. And third thing is actually also about oxygen. We may be achieving to a very unique oxidation condition that's not easy to achieve in the two-step method. So maybe it's because of this reason that we can achieve a higher TC. So another trick that we used is this interface structure management. Usually, if you just after if you use this as received substrate, it's a 214 structure, so you have a single layer on top. And then if you grow the bilayer directly, and then some may be forming this nickel aluminum bilayer, forming this bilayer structure. Some may be growing directly, so you have a different mode that's with a similar energy, so they may coexist and make the film not so crystalline coherent. And a way is to anneal the substrate. If you anneal the substrate, it will automatically form a bilayer of or bilayer of aluminate at the surface of the substrate. And then you grow bilayer nickelate on top. It's pretty coherent. So this is actually the method that we use for our first report. And but this method, the productivity is pretty low because this annealed substrate, the quality is not so consistent. I think it's about several tens of this substrate annealed is good quality enough. So the productivity is very low using this method. So and then we use this new method is to deliberately grow a monolayer first to form a nickel aluminum bilayer structure. So this is kind of a reconstructed interface, or you can also say this is a buffer layer. And after this, you grow the bilayer, and it's pretty coherent on top. And so this can be clearly seen in the TEM. Underneath, this is the substrate, and this is the interface buffer. This bilayer you can see. The lower layer is aluminum, and the upper layer is nickel. So this is aluminum nickel bilayer structure. Yeah. Yes. So in that case, we also use this method. Yeah. So this is the buffer, or the interface reconstructed interface. It's all the same. So so for this buffer, we think it's inert. It's pretty insulating. So we measured it's completely insulating. So it's just for a structural thing. It's not affecting the superconducting property above. Yeah.
Now you have a new sample with
Mm-hmm.
And what's the difference between the first one and the new sample with 60?
What's the difference? Yeah, so improvement improvement is several stuff is improved together. So we are not 100% sure what is making it really enhance the TC. So first thing is the crystalline structure is greatly enhanced. This is 3 different different regions of the same sample, TEM images. This field of view is the largest possible that you can still resolve atoms. If you use a even larger field of view, you can't see atoms. So using this largest field of view and taking 3 different regions, you can see this highly ordered cations and also atomically sharp interface. And using X-ray diffraction, it is also quite obvious that our crystalline structure is greatly improved. So this is a synchrotron X-ray diffraction. You can see this oscillation is oscillating all along. And this is the comparison between this one and also this reference 6 is our original report, the first Nature paper report. So you can see that it has a pretty obvious enhancement of these X-ray diffraction peaks. Below this one is RSM, reciprocal space mapping. The qualitative sign is that this peak aligns with the substrate peak at this X direction. We know that it's coherently string. Another thing is at these 4 different directions, we see this QZ is also consistent. So this may be this is consistent with that it's a tetragonal phase, but still XRD is a quite macroscopic measurement, and this peak is quite broad, but it looks like a tetragonal. And for this reciprocal space mapping, if we also compare with our original report, you can see this film peak is also greatly enhanced in intensity. So that means the crystalline structure is much better. So another different thing is we think that we are achieving a quite unique oxidation condition. We grow a lot of samples. Here are 90 samples, all with 0 resistance above 15 Kelvin. So some are higher in onset TC, some are lower or closer to 40. It's about basically from 40 to 60 Kelvin TC. And what we see is that in this 60 Kelvin stuff, you basically have a higher resistance, and so normal state resistance is slightly higher. So we think this is less oxidized compared to the old samples that's around 40 Kelvin. So this is our guess that in the 40 lower TC side is over oxidized, and in the higher TC side it's more optimally oxidized. Another very important feature is the normal state RT curve. For those 60 Kelvin samples, it's more linear. So this is 63, this is 60. So these 2 samples, you all see that they are quite linear in the normal state. And in comparison, these are lower TC, like 46, 38. You see the normal state looks more like a T square, this Fermi liquid behavior. Yep, so that's all of my talk today. So we use a new method that we call the gigantic-oxidative atomic layer by layer, and we engineered this nickelate hybrid superstructures. Some are superconducting, some are not, and we also measure the RPES of all these structural variants. And then using this growth method, we also push to an extreme non-equilibrium condition, and so to get a TC enhancement to above 60. And before ending, I would like to also advertise for the NSR National Science Review. I'm the section. I'm a editor. I'm in the editor group of the mathematics and physics section. This journal is established in 2014. So its aim is to be the highest quality this scientific journal, and quite recently the amount of publication is climbing very quickly. So next year maybe there are 700 publications, and it's actually already a conservative expectation. Very likely in next year, or at least the year after, we'll have basically the same level of amount of publication compared to science. And so the impact factor is also climbing fast. And now the level of the manuscript being reviewed, we basically consider if you are about the same level of nature, like nature materials or nature physics, this kind of level, and you will be sent to review. Also the national policy is supporting the growth of these journals. So welcome if you have good paper, please submit to National Science Review. It's growing very fast. If you submit right now, maybe you get passed easily compared to like 2 years later. Yeah. I don't think there's a very strict this kind of limitation. And so this journal begins with all review paper, and afterwards some research article. It's becoming the main body. Yep. Okay, that's all of my presentation. Thank you very much.
Professor Chin has given a very nice talk. Now it's time for questions.
I guess a lot of questions is asked along the.
We have sufficient presentation.
我可以用5分钟了。这个60K 的这个新的这个样子，当然就像你说，肯定很多关键的因素在。但是就像我跟你教的说，可能下面这一条214就挡住了这个丝的扩散，是吧？
是，对。
使得上面的这个摆列这个327呢里面的这个假如几乎是跟包差不多。
很有可能，对。
对机器是这样。
对。
还有很多其他关键的结构方面的。另外呢，就是你挑到这个氧含量过度的氧的环境里面的肯定会导致这个失超，这个是电子比态的。这个其实最近留意做这个工作，我参加的，就我们就具体算那个例子，7.5。如果是变成7.5，那确实是非常比态。就是惯电机也很弱，然后
就没有超导了，是吧？
然后即使我们把相对调强了，它也只能会出现某种特殊的结构。你的基础的，基础的，一定是对的。所以这个跟你讲的就非常清晰。
对对，我刚刚也跟卢老师讨论了一下，就这个，我觉得就很可能是这种情况，对。对对对对对。
我记得好像是丹佛还是哪个地方，他们说长在这个 tensor 或者是这个 pressure 比较小的这个情况下就不超导，但是压一压就超导，是可能不一定是丹佛他们。
日本的，对对。
所以可见这个是还有可调节的余地。
绝对有，对，绝对有，对。
就像你说的，长了这个40-30这个超，那也许压压更难超。
是是是，对对，肯定是这样的，对。对这个，对这个就是对要仔细摸索，我们一般就是在6纳米的这个非常 consistent 的，我们全部都是在这个条件下来做优化的。但就是6个 bilayer，6个 bilayer，3个 unit cell，然后如果更厚的话呢，我们也有试过，但没有非常系统。就它基本上就是也可以超导，然后呢，可能电阻会低一些因为可能你总体厚度变厚了嘛但是至于如果太厚的话，它会不会说在厚度上面会有一些不均匀也许会有，但这个可能要再研究，对。对，我们涨了很多这个1313，然后呢，就发现它比较稳定一些它没有那么不稳定，然后都是类似的这种行为，它实际上跟 bulk 是一样的，所以呢，我们还比较有信心应该对，就是因为 bulk 是大概是在19巨帕开始出现有超导。然后我们这个薄膜这个 compressive strain 如果你只考虑 in plane 的 lattice constant change 的话，大概是约等于15个巨帕的样子。对，然后他们的那个17巨帕的结果，就是比这个稍微更 metallic 一点，然后11巨帕的就比这个稍微更 insulating 一点就是这个是刚好 in between， 就实际上跟他们非常符合。对。333就是还没轮到他，对，还没就还要时间，对。
如果没有进一步问题的话，让我们再次感谢陈老师给我们的报告。